Hey, this is Brock Lemires, and in this video I'm going to continue talking about AC signals and specifically give an overview of circuit analysis basics. Okay, so when you have a circuit that is driven by an AC source, we use this symbol right here. So you have a circle and you put, a little sine wave in it, of course. So to represent that it's AC, okay? And then what you do is you, of course, label it. So let's just say that this was Vs of t to represent, that's a source, lowercase because it's time varying. And then we'd still put a polarity on it, okay? So you still put positive and negative on there. And we know that the current's going to flow in both directions, but we do need, a reference of when t equals 0 is and when the sine waves start in here. Okay, so then there's some interesting things or some really cool things that happen with AC signals and circuits that make life pretty easy, okay? Not easy, but easier. Okay, so here's the first big thing that happens. When you have this circuit right here, a single source, okay, the frequency of the source is the same as the frequency in all the passive components, okay? So if you have a sine wave over here, okay, you have some sine wave and it has some frequency, let's say 1 kilohertz, okay? What the signals, the voltages that you'll see across these resistors will also have a frequency of 1 kilohertz. It's constant everywhere, okay? So the signal will be a sine wave over here and a sine wave over here, and they will be also 1 kilohertz, okay? So that makes it really nice because we can actually, think about, we don't have to actually worry about the frequency being different everywhere, okay? So that's the first thing to keep in mind. The second one is that the frequency is also the same in the voltage and the current. So when you do an analysis on here, you don't have to worry about, the voltage is 50 hertz and the current is 60 hertz. It's no way. It's always the same frequency. So if the voltage is 60 hertz, so is the current. Okay, so the current is fixed. Not current, the frequency is fixed. Here's another important one. Passive components don't alter the frequency. And what I mean by that is that if you had a source that's at 60 and you put a resistor in there, it doesn't dampen the frequency and make it 59 or 58 or 57. It's always fixed at whatever the frequency of the source is. Okay, so we don't change the frequency by putting other passive circuits in here. Now you could say, well, what if I had another source? Well, if you had another source, you would basically combine the two sine waves, and then that would be the source frequency or the source signal that would then be replicated throughout all of these. So the frequency doesn't get altered by any of these passive components. And then finally, the really neat thing is that all the circuit analysis techniques that we've looked at still work. So they all work the same way. Ohm's law works the same way, KCL works the same way, and KVL works the same way. The reason that this frequency thing is such a big deal in AC analysis, this is actually called sinusoidal steady state analysis, and that just means that you have a constant sine wave that's going forever. The reason that that's so cool is because in electrical engineering, what you can do, in math, you can just take that frequency, just go ahead and put that off to the side, and then you can figure out ways to analyze the circuits and not worry about the frequency. Okay, and then when you're done with the analysis, you can take the frequency and plug it back in. Okay, and that allows us to do a lot of cool stuff, such as transform, the sine wave function. We have this V of t, and we've described it as V peak times sine of 2 pi f t minus phi plus v offset. That's a lot. There's a lot going on in that equation right there. And so if you could somehow take this and just say, you know what, the frequency is we're just going to remove that frequency, then you can just deal with things that really you care about, such as what is the amplitude, what is the phase, and even the offset can be set aside, or what is the offset. So anyway, that's what you have. Okay, so let's do a quick example to kind of show that this works. What if I took this circuit and let's say that I had this was 50 ohms and this was 100 ohms. And I want to plot, or I want to calculate what the voltage is across R1 and R2 are. And also I'd like to know what the current is. And I'd actually like to plot it out. Well, here's what we're going to have. So let's say that we have this source right here, and let's say that its amplitude is 10. Okay, so it goes from 10 to minus 10, and its frequency is 1 kilohertz, and there's no shift. Okay, there's no phase shift and there's no offset. So I can come along and I can write this. Let's go ahead and write our Vs of t is equal to 10 multiplied by the sine of 2 pi 1k, okay, 1k times t, and that's it. There's no phase shift and there's no offset. And what I want to do is I want to say, well, what is the voltage over there? Well, I can use KVL, KCL, voltage dividers, or currents dividers to find that. So let's do a voltage divider on this voltage right here, which is going to be plus or minus V1. So I can say V1 is going to be equal to, and I can place this off to the side. Okay, so I'm just going to place that off to the side, and I'm just going to use the amplitudes to do this. So I can actually say, okay, V1 is going to be equal to 10 multiplied by, okay, that's the source going in there, and I can just say 50 over 50 plus 100, and I can actually get, one, so that comes out to be, you can kind of do it in your head there, so it's 50 over 150, so it's 1/3, so it's 10 times 1/3, so it's 3.33 volts, okay? And look what I did, I just used the amplitude there because I was able to put the frequency to the side, and so it's like, oh, okay, that's great. Well, now if I wrote the expression for that voltage, it would simply be this, it would be 3.33 times sine of 2 pi 1k, because the frequency didn't change, t, and that's it. So I just figured it all out. Life is good. If you wanted to formally keep all the sine wave stuff in here, you could write this as, okay, I'm going to have 10 times sine of 2 pi 1k t multiplied by 50 over 50 plus 100. And that technically is fine. But notice that this just didn't have any impact on it other than we just carried it through in our math. And so that's the answer right there. Now, if I want to do V2, I could essentially do either another voltage divider expression, or I could just do KVL, because if I did KVL, what I'd have is, I have a voltage rise here of Vs, and then I drop across our V1 and I drop across V2. Well, it's pretty easy to know that V2 is simply going to be 10 minus 3.33. Okay, so if I sum my rises and sum my drops, I'd have 10 is on one side. Let's do it officially. So I'd have 10 is equal to V1 plus V2. 10 is equal to 3.3, and then all that other business, plus V2. And so V2 is equal to 6.67. Okay? Well, if I wrote that out, I'd have this. I'd have V2 is equal to 6.67 times sine of 2 pi 1k t, and I'm done. So there is now V2. Now, how could I get the current? Well, check this out. Let's combine these two resistors in series. So I could replace that with an equivalent resistor that looked like this, that looked like 50 plus 100, so I could have 150 right there, 150 ohms. And then when I do the current, I can just use Ohm's law. So this is going to be I of t, and this is Vs of t, of course. And all I do now is say V is equal to IR. Well, the voltage across that resistor is 10, and my current is going to be I of t multiplied by 150. So I got I of t is equal to 10 divided by 150. So let's get out old buddy here and see what that is. Boom, boom, boom. So I got it right here, and I go, hey, 10 divided by 150, and the answer is 67 milliamps. And now if I wrote that out, I'd have I of t is equal to 67 milli multiplied by sine of 2 pi 1k t. And life is good. There's no phase shift introduced into this because we're just using resistors. There are components that might have a phase shift, but remember, resistors don't have any phase shift, okay? So that is really how you can do all this stuff. It's pretty cool. And another thing that's really cool about it is you could do this whole analysis using RMS if you wanted to. So if you came up to a circuit and you said, hey, I got I got a circuit here, and it's like, oh, I got plus or minus. No, excuse me. I go like this, and I got a sine wave. I got plus or minus. And I got VRMS, and I said that's about, that's 120 volts RMS. And I had, something like this. You could do all that KVL and KCL around this loop using just the RMS voltage, and then you could plug in the frequency later with the whole sine of 2 pi ft minus phi stuff going on. Okay, so you got to keep track of whether you're using amplitude or RMS, but all these circuit techniques still work. Okay, so that's kind of the basics of circuit analysis when you're using AC signals, and specifically what we call sinusoidal steady state, which is where you have a sine wave that's continuously operating forever and ever. Okay, all right, so that is it, and see ya.